Hi there, this is the pre-class reading video for class 19 in which we are beginning chapter 7 on work and energy, which opens with a photo that actually is Yelena Isinbayeva from Russia doing a pole vault. Her record was 5.06 meters. So how can pole vaulters reach such great heights? You have to go really fast. Basically, one of the things they're doing is going really fast, so they have a lot of kinetic energy, and they're bending that pole so that it stores a lot of elastic potential energy, and then they're converting all of that energy into gravitational potential energy to get them up and over the bar. Section 7.1 is called Work and Energy. And as usual with this textbook, she likes to begin with the observational experiments. And the purpose of the observational experiments is to give you an idea of how to understand these concepts, how we can play around and make observations and lead us to these formalizations. So, which is really how science works. But if you want, you can skip ahead a little bit. This is talking about different kinds of energy. And it gets to a real definition of work, negative and zero work. And it really gets into it here. So when an external force is in the direction of an object's displacement, we say that it does positive work on the object. When an external force points opposite the object's displacement, that force does negative work. And if it points perpendicular to the object's displacement, the external force does zero work. So what we have here is a system with maybe a rope is giving a force on it. Imagine that system, this box here, moves some displacement. So the displacement is a vector, displacement of the system, S. The force is a vector, and there is an angle, theta, between those two vectors. So our equation for work of the rope on the system is that force, the magnitude of the force times the magnitude of the displacement times cosine of theta. And so that's equation 7.1, which is a good one to have on your aid sheet. And I guess cosine can be positive or negative, and that's what makes the work positive or negative. So force is always positive, it's the magnitude of the force. D is always positive, magnitude of the displacement. And then cosine becomes positive or negative depending on if theta is less than 90 degrees or greater than 90 degrees. And that makes W positive or negative. So then there's some examples of all that stuff. Section 7.2 is called Energy is a Conserved Quantity. So what that means is that there's some total energy, which is the sum of all the different forms of energy. Here we see E is equal to kinetic, plus gravitational potential energy, plus a spring potential energy, plus internal thermal energy. If the system is isolated, meaning that there's no work being done in the system or the system isn't doing any work, then the energy is going to be constant. And so, called conservation of energy, you can use this work energy bar charts. This is actually a little bit easier than the momentum bar charts because energy is not a vector quantity, so you don't have to keep track of the x components and the y components. So there's a few nice examples and toolboxes showing you how you can use these bar charts. So positive just means positive energy. Negative can mean like negative work or well, I guess only work can really be negative. Actually, negative potential energy as well. It's possible. In section 7.3, they finally give equations for gravitational potential energy and kinetic energy. And so, okay, so we do say, I guess, if you think about the work done by the force of gravity on an object, that if an object, like this cup, is going up, if its displacement is up and the force of the earth on the cup is downwards, then I guess you could say that the work done by this external gravity force is negative if it goes up, and I guess it's positive if it goes down, because that displacement vector is either opposite the force of gravity on the cup or it's in the direction of the force of gravity on the cup. But that's not how we really deal with the force of gravity. With gravity, what you like to do, the best way to approach it, and this is the approach of Chapter 7, is you take your system to include the Earth. And in that case, we say that there is this U sub G, gravitational potential energy. And we say that, since the Earth is part of the system, we don't take into account work done by the force of gravity. That's an internal force because we include the Earth. So instead, we say that there's a gravitational potential energy, which is m times g times y, where y is the height. And that's the negative of the work done by the force of gravity, okay? It's the energy now that is stored in the cup. So if the cup is higher, then U sub G is higher. And you don't use work done by gravity because it's part of the system. So what you do is when you're conserving energy, you say that the work done by gravity is 0 because it's an internal, and gravity is an internal force here. And your conservation of energy just includes the gravitational potential energy, initial and final. Hopefully that makes sense. I'll explain it more in class. And then lastly is this kinetic energy. It kind of motivates it a little bit of work and how that's going to change things. You can use a kinematics equation and you end up finding that kinetic energy is 1/2 times m times v squared, where v is the speed of an object. So this is an always positive quantity. It increases as the speed increases as the mass increases. Actually, it increases with the square of the speed, and it's a really useful energy. And what's interesting is that kinetic and gravitational both have the same units. It doesn't look like they would. It's going to be mass, kilograms meters squared per second squared. That turns out to be the same as newtons times meters, and we have a special name for it. We call it joules. Joule, named after, I think, a physicist whose last name is Joule, but we put a J there for the units of energy. And there's some examples of that. And that's the pre-class reading for class 19. Hope to see you in class. Bye for now.